Good afternoon, everyone. Welcome to another session of EI Live K-12 for students and educators. So my name is Cassie, and I direct educational and outreach activities across the Earth Institute, and we're really excited to have all of you joining us today. So for those of you who are tuning in for the first time, if you're not familiar with the Earth Institute, our core mission is to foster a greater understanding of the science behind climate change and sustainability, and what we as global citizens can do. So experts that make up the Earth Institute are actually quite interdisciplinary and diverse. They include economists, business and policy experts, specialists in public health and law, and earth scientists, of course. And the Institute is made up of more than 24 or so research centers and several hundred people who collaborate across many different departments at Columbia University. So what we're hoping to do with these EI Live K-12 sessions is to introduce you to all of our interdisciplinary work directly through our scientific experts. So we're going to have weekly sessions up until the end of June. And if you'd like any further information about those sessions, feel free to contact me directly. Each week is going to be a different topic, and each topic is going to have a certain age range that is appropriate. Although I think we have had everyone from kindergarten students up to retired individuals. So we really are hoping that these sessions are reaching a broad audience. So today we are very lucky to have Spencer Hill from Lamont-Doherty Earth Observatory, which is the largest center of the Earth Institute. He's going to be speaking to us about his work. And once we are done with his part of the presentation, we'll open it up for Q&A. And if you do have any questions that come up during the presentation, feel free to use the Q&A box and not the chat box. We've disabled that function. So just use the Q&A box. I'll keep an eye on the Q&A box throughout the session, and we'll keep track of questions, and we'll be sure that there's plenty of time for everyone to ask their questions. We're also going to have a special guest from NASA GIST, the Goddard Institute of Space Studies, telling us a little bit also about the NASA resources that are available for students that are related to Spencer's topic. So Spencer, without further ado, why don't you take it away?
Okay, thank you very much, Cassie. And thank you everyone for attending. As Cassie mentioned, I'm a research scientist at Lamont-Doherty Earth Observatory. I mostly study the atmospheric circulations on Earth in low latitudes, what are called monsoons. But today we're going to be taking a much broader picture of what goes on in Earth's atmosphere, Earth's oceans, even the interior of the planet, and even other planets besides Earth. And what I hope to convince you of is that these features, these circulations, are fascinating and beautiful. And I also hope to convince you that we can understand them, we can learn about them using very simple models, tools from around even your own house and kitchen. We can understand them using these very simple things. So I mean for this to be a lot of fun. I hope it is. But we're also trying to be learning, thinking actively the whole time. So this isn't just a magic show playing around. Hopefully we're going to be learning as well. So keep thinking, play the scientist at home while we're doing this. Okay, so let me put some slides up. Okay, so why are there swirls all over? If you look at Earth's oceans and Earth's atmosphere and inside of the planet and other planets, we see swirling features everywhere. We see them here, satellite imagery of the open ocean. And these different colors are actually caused by phytoplankton blooms. The lighter colors are where there have been blooms of these tiny microscopic ocean creatures. And they trace out the flows of the ocean. And you can see all of these swirling eddies, we call them, all over. They happen in the ocean, open ocean. Sorry. Oh, there we go. They happen just off the coast. You can see here, this is in the Barents Sea, maybe the Baltic Sea. This incredible spiraling eddy right here in the middle, a smaller one further off. You can see these little clouds popping off the land as well. They happen in very hot and arid regions. So here in the Gulf of Aden, the Horn of Africa, and these massive deserts of the Middle East. On the other side, we see these incredible phytoplankton blooms in between. Again, all this swirling, twisting features. And they happen in really cold places. This is, I can't remember off the top of my head where this is, but you can see all of these icebergs that are drifting along this giant swirling eddy in the ocean. And given that it's icebergs, it's a very cold place, probably somewhere near the North Pole. So they happen all over the ocean, these swirling eddy-like features. They happen in the atmosphere too. Here we see from the Discover satellite, a snapshot of Earth's atmosphere from a particular day within the last couple of years. And you can see we have this very thin band of clouds along the equator. That's called the Intertropical Convergence Zone. That's what I actually mostly study. But up here, closer to where we live, if you can see, that's the California coast here. We would be sort of over here. And it looks like California is really getting slammed by this swirling eddy here. And Alaska is getting hit by a big one too. We see here a wide array of different cloud formations. This is in the low latitudes. And you can see these individual towers here. You can see a little line of them here. You can see these big towers that have created these anvils, these flat, broad features high up in the atmosphere. And you can see there's these incredible motions happening on all these different scales, and they're interacting with one another. And I hope you agree that they're truly mesmerizing. At least I think so. They can be dramatic. This is a shot of an eye of a hurricane. This was Hurricane Dorian. This photo was taken from the International Space Station a few years ago. And you can see this incredible imagery. The technology of the satellite and space station imagery we get now is so stunning. You can see clearly all the way through this eye of this massive hurricane down. You can actually see the open ocean and parting between the clouds there. You can see swirling storms in places like the Midwest US, which is where I grew up. So over this cornfield, maybe somewhere like Kansas, which is my home state, you can see these incredible swirling storms that generate these massive rainstorms and sometimes tornadoes. And they're scary when they come and the tornado siren comes and you have to go in your basement, but they're also truly beautiful. They can generate some pretty incredible stuff closer to home now. So I'm here in New York City, and you can see from a couple summers ago, this image of this incredible roll cloud coming over the island of Manhattan. So for reference, here is the Empire State Building, and then uptown Central Park is sort of over here, and Columbia, where most folks are in this institute, would be up further that way, past that side of the screen. And they happen on other planets. This is an image from the Juno cam, the Juno spacecraft, the space mission that went to Jupiter and brought back all of these incredible images. This is just one of thousands you can find that you could spend all day looking at. And you can see these swirling storms and features all over that look a lot like the ones in the ocean that we saw and in the atmosphere on Earth. So that tells you that maybe they're related somehow. And then coming back to Earth, these storms can bring, this time of year, lots of snow, right? So this is actually from 2017. You can see the snow cover over this the Northeast US. So here's Long Island. Here we are down here, and you can see a huge amount of snow everywhere. And we want to understand what are the storms that cause this kind of snow. Because it's not just in the past that happened, it's happening right now. For those of you not in the area, we've gotten 20 plus inches of snow, a bunch of storms in a row lately. And I'm going to stop sharing that now and show you in real life. We're going to switch to the real world now. I'll show you the view from my back window. You can see the snow everywhere. You can see our snowman. So we want to understand what causes all of these things. So to do that, we are going to go on a space mission. We are going to launch into space and look at Earth from far away so we can understand where all of this swirling comes from. So we are going to hitch a ride on a space shuttle. Any spaceship, any space mission, you need to be safe. You need to wear your space helmet. All right, so we got our space helmet on, our space suit. We launch off to Earth, okay? Okay, so that's liftoff. Okay, we had a great Houston, we are a go. We're blasting off. We are out of Earth's atmosphere. We're looking back at the space from the spaceship. We see Earth. And bear with me, Houston. Okay, and we've made it out. We're doing a spacewalk. And keep bearing with me. Okay, and now we are out in space and we are seeing the Earth. Okay, so here we see the sun is coming from in front of Australia there. And what is the Earth doing? It is rotating. Oh, there we go. It is rotating. This worked better before. There we go. Okay, so we see it's good morning, the US. Good morning, Japan, etc. So as the Earth is in space rotating around every 24 hours, that's going to be crucial. That spinning of the whole planet turns out to cause so much of this other spinning. So now we're going to do some more experiments. We're going to go back into the spaceship and do some experiments on our countertop to figure out more about that. Okay, so we're ending the spacewalk. We are making our way back into the laboratory of the spaceship. And okay, we made it in. It was a successful spacewalk. Houston, all things to go. And okay. Phew. Okay, great one. So we're in now. We can take off our helmet. We're in the spaceship lab, which looks a lot like my kitchen, ironically. Okay, so we want to understand what the spinning of the Earth does to the fluids, the water in the ocean and the air in the atmosphere. So why would spinning matter what does it matter that it's spinning at all? Well, one way of thinking about that that's helpful is with a familiar toy top, right? Every kid had one. So what happens when a top is not spinning? If I let it go, it falls over. It falls over again. It's the world's most boring toy. Where does the fun of a top come from? From spinning it. Now what happens if I spin the top? It stays up, right? So this top moves around a little bit, but that spinning somehow keeps it aligned vertically. If it starts to wiggle one way, it sort of gets pulled up. If it starts to wiggle the other way, it gets pulled up, right? You can even bump it a little bit and it'll still mostly keep spinning. So we might think that Earth spinning is doing something to the same effect. It's causing the water in the ocean, the atmosphere, air in the atmosphere to stay upright. Okay, so if we want to model that, if we want to make an experiment to test that, we can't unfortunately just pour water on this globe. That's not going to work out well. So we need to come up with some other way of doing it. So we do the following. I have here the globe that we saw from outer space, and we see it here and it's spinning. And I'm going to attach our friend here. Her name is Corey, short for Coriolis. And Corey is going to ride around on the planet just like you and I are riding around on the planet. And then what I have here is a flat Lazy Susan, just a rotating tray in your kitchen. But look what we have here. This is a map projection, so you can see it looks just like we're looking down on Earth. So the spinning of the Earth, we can simulate, we can model through the spinning of this flat tabletop. And to make that especially clear, we'll put Corey's twin on the spinning table. So they say hi to each other. Hi, Corey. Hey, twin. We're both spinning, and it's like exactly the same. So that's great, because then what? We could put something on this. We can put a tank on here and spin it, and we can put water in this tank. And now we finally have a rotating system filled with water, which I'll fill up right now, that we can use to actually simulate the rotating fluids in our Earth. Okay, so before we do that, you might think, how is this few inches of water, how can we possibly simulate the atmosphere with such a small depth of water? So I pose this question to you. If Earth was the size of this globe right here in my hand with Corey on it, if it was to scale, how thick would the atmosphere be around this globe? Would it be an inch? A tenth of an inch? How big? Think of an answer. Make a hypothesis before I reveal. The answer is that it would be as thin as this piece of paper. So in other words, the atmosphere is as thin as the edge of this paper if it were the size of, if the Earth was the size of this globe. Our atmosphere and our oceans are very thin compared to the size of the Earth. So it's okay that we don't have a deep depth of water. Okay. Now, normally the next step would be setting up my little motor that runs and spins this at a constant rotation rate. And we build that out of Legos. I'll show you guys how to do that later. But Houston, we had a problem and my Lego thing is not here right now. So I'm going to switch over to a video that we made that's going to show you how to do 3 different demonstrations of things in our rotating atmosphere and rotating oceans and rotating interior of the Earth. So, and we'll stop at one point where I'll do the non-rotating version here to give you some real world demos nonetheless. So let me cue this up. Okay. Share. Okay, so here I am at the DIY-namics website. DIY-namics stands for Do It Yourself Dynamics. And this has tons of great resources for all these kinds of demos that and experiments I'm doing today. So we'll click on the YouTube page. And here, this top one was a video that we put together for Lamont's open house just this past fall. So I'm going to narrate and stop and narrate this as we go. Okay. I'm going to pause it here and explain the setup. So this should look a lot like what you just saw in my kitchen. I mean, the spaceship lab with the Lazy Susan, a tank of water in it. The only thing I was missing was this motor that I explained, the Lego setup. But you can see that that Lego motor drives this at a constant rotation rate. And there's a camera on top, a phone, that gets us footage of the system that's rotating with it, just like we're rotating with the Earth as it spins. I think I covered this mostly already, but it's good to review. Once every 24 hours, that maybe sounds slow compared to the spinning top, but it matters in a big way. So we're creating a scientific model, a real world analog model of Earth's atmosphere, of Earth's interior, of Earth's oceans, using this tank of water. Now, maybe you should have mentioned this up front, but our atmosphere is a gas. How do you model a gas with liquid? Well, both of these are fluids. Liquids and gases are both fluids. And it turns out for the things that we care about here, fluids act the same way. So we can use water to study the atmosphere here too. So in these three experiments, we'll progressively add more things into the system that happen in the real world. Okay, so here's where I'll pause the sharing and do the real world version to show you that it's not all some Hollywood magic. Okay, so what we've got here is just this plain old tank of water. It's not rotating. And what I'm going to do is this is the tank version of the non-spinning top. The boring falls over. I've got blue food coloring and I've got red food coloring. And I'm just going to put some drops in there and see what happens. Okay, so what do we see? We see red and blue, and we see stuff going everywhere. From the side, we see it going in all the directions. There's parts that are purple where the red and blue have mixed, and there's really hardly any clear water at all, even after just a few seconds. It's going side to side as well as up and down. All right. Now we'll go back to the video. and get another shot of that as well as the rest. Now we're looking from above. See the same thing as in my tank here. Now we crank that motor on and we do the same thing. And now look what's happening. Remember the top that stayed upright when it was spinning. These columns, they don't go anywhere. They stay upright, just like the spinning top. So this matters most of all actually inside of Earth. So this schematic shows Earth's mantle, this outer layer, the inner core in the blue here, and the outer core, which is just filled with magma that also is a fluid. And what do we see in this outer core? Do you see it? These columnar structures, these red columns that go up and down. These are from the Earth rotating, just like we saw in the tank just now. Here's another sort of visualization of that from a different simulation of it. And this structure within the sort of magnetized iron core creates our magnetic field. That creates beautiful things like the aurora borealis, the northern lights, and much more importantly is necessary for all of our modern telecommunications, all of modern life, basically. Okay, now we go from Earth. We're going to get back in the spaceship, but I'm running low on time, so we'll cut the side special effects. And we made it to Jupiter pretty much. Okay, so we're at Jupiter, and we want to see what happens when we add a little stirring. So what happened there was the system is rotating. We put in the dye just like the last time, but now we're just going to swirl a Lego piece through there. And what do we see? We see these incredible spinning eddies, right? I'll pause. You can see here's one that just formed inside of one that was already over here. You see another one forming over here. You see them moving around next to each other. You see them interacting with each other. You see these long filaments between them. But you also see red right next to blue, right next to red. You see these thin layers, one right next to one, and they don't mix together so much. And there's still clear water over here. And you see that these eddies live for a long time. They don't just disappear right away as soon as they form. What does that remind us of? How about the Great Red Spot of Jupiter? This storm is bigger than our entire planet, and it's been around for hundreds of years. And there's all sorts of these incredible swirling eddies on Jupiter that look a lot like, and we can think of in a very simple way as being very much like the swirls we created in our tanks. The difference is those storms are moving at like 400 miles an hour. Okay, last thing. We want to finally answer what's up with the storms, the winter storms here. Why is there so much snow in our yards right now? So we're going to, in addition to the rotation, we also know that it's a lot colder at the poles on Earth than it is at the equator. So that north-south temperature contrast is going to interact with the rotation. And let's see how. So our version of the North Pole is a can of tomato paste that we put in the freezer and took its label off. And that's what you see in the middle of this one. And otherwise, we didn't stir this one at all. We didn't, not like the second one where we stirred it. This one, we just did the cold can in the middle and the rotation, and then we put in the dye and see what happens. We put blue in the middle to make you think cold, red on the outside where it's less cold. And you see these incredible swirling eddies forming right away. And they'll quickly take up the whole system. So you see the cold water, for example, where my mouse is, flowing out from the cold source and going out to where it's warmer. And vice versa for the warm places. And so this mixing, these eddies transfer heat from the cold to from the warm to the cold place, basically. And that's just like mid-latitude storms on Earth, which you can see in this satellite composite. This is Southern Hemisphere winter, but you can see this curling eddy here, the ones highlighted in the oval here. And they bring a lot of snow with them too. So Norris Koo gets all the credit for that video. And so I'll end with one last thing, which is sharing something on, oh, right, I was already on Firefox, sorry. So what's up with all the snow out right now? Well, we can look, this is a website that visualizes current weather data, and you can see the wind patterns that are shown here at the surface, and the colors, the greens and reds, give you stronger winds. And what do we see? We see this great big storm, this swirling storm that looks a lot like those ones in the tanks and the satellite composite from before. And we see that it's bringing in this cold air. The air is flowing from the north down to New York, where we are right here. And we've been getting one after another of those this winter, and that's why we've had so much snow. And if I move a little bit, you can see, just like the tank was full of those eddies, the Northern Hemisphere, where it's winter right now, is full of those too. These swirling eddies caused by the rotation combined with the temperature contrast. Okay, so that's it. Let me just shout out one last time the DIY Dynamics website for more on all of this stuff, as well as a partner of ours, Miriam Glesmer, has a program called Kitchen Oceanography, where you can do all sorts of other demos, at-home demos of earth science things, not all of them rotating, but cool nonetheless. And I hope you all learned something. Looking forward to chatting with you in the Q&A, and thanks a lot.
Great, thank you, Spencer. So let's turn it over to actually our NASA colleague, Rosalba. For our viewers, if you do have any questions, feel free to type it into the Q&A box. I did put the DIY Dynamics GitHub website in the chat box. So if you did want to take a look at what is on the site and what Spencer and his colleagues have done, that would be the place to go. So Rosalba, if you want to take over and let us know what NASA resources there are to also help us better understand our ocean currents and circulation. So I think you're on mute. Perfect. There you go.
Thank you. Yeah, sorry about that. I have the phone and the computer. So yes, thank you, Cassie, and thank you for the opportunity to share about some NASA resources. Thank you to Spencer. I had so much fun with that. I want Spencer to be my teacher. So yes, so my name is Rosalba Giarratano. I help support NASA's Office of STEM Engagement at the Goddard Institute for Space Studies. And I just want to quickly share with you about some supplemental resources that may be fun for you. So today I want to highlight NASA Space Place, my NASA data, and the Scientific Visualization Studio. So NASA Space Place is designed for upper elementary aged kids. And so basically it's a website where you can find online games, hands-on activities, articles, videos, and it is available in English and in Spanish. And in addition to all these resources for the students, there are also resources for parents and teachers. So if there are any parents or teachers also tuning in, definitely this is a very useful website. So on the screen, I am highlighting just one of the games that has to do with ocean currents for the students to learn about how different factors affect how the oceans flow, like temperature and salinity and all that. It also has links to, for example, a mission, SMAP, an NASA mission that measures salinity in the oceans. And so it also includes videos. I think just this page alone highlights a couple of videos. So again, a very cool, fun website for you to browse and explore. The next resource is My NASA Data. So this one is mostly for teachers. So it is a great compilation of lesson plans, story maps, activities about Earth science. So it is divided in spheres, so you can look for topics in the atmosphere, biosphere, cryosphere, and so on. The lesson plans and activities are designed for grades 3rd to 12th, and they are designed to support students in analyzing and interpreting real NASA mission data. So I am on my screen, I am highlighting some of the resources that have to do with ocean circulation. So it has links to several videos, STEM career connections, articles, and much more. And last but not least, I also want to highlight NASA's Scientific Visualization Studio. So this studio works very closely with scientists to create visualizations, animations, and images to help us understand Earth science and space science better. And another cool thing is that all these visualizations and multimedia products are free to download from the website. So you can just go ahead and load all these visualizations. I'm just highlighting one of them, but there are thousands. So this one that I am highlighting is a fragment of what was also used for another video for Earth Day 2020. So it is showing the Gulf Stream ocean current pool. And yeah, so there are thousands of visuals that you can download for free. And that's it for me today. Thank you.
Perfect. Thanks, Rosalba. So great. We have a very good question in the Q&A box, and Spencer is going to answer this live for us. And if you do have additional questions, feel free to type it into the Q&A box. Spencer.
Thanks. I'll just say, after Rosalba's talk reminded me, if it wasn't clear, most, if not all, of the stuff that I showed you was NASA imagery. It was from the Earth Observatory Image of the Day. That's a great website. Or shots from the space station that the space station Twitter account or astronauts tweeted. NASA is such the go-to for great visualizations and imagery and stuff like that. So yeah, keep it up, gang. Okay, so the question is, did the mini storms that were created in the experiments have something to do with the torus? That part I don't understand, but I think I understand the rest. In the experiment, we could see the mini storm because it was colored with food coloring, but why can we see them on Jupiter and other planets that aren't made out of food coloring, basically? Are there invisible storms that the human eye cannot see? So the answer is yes, definitely. It's not always the case that there are tracers, which is what we call it, that make these circulations visible. In those ocean pictures, it happened to be that there were the phytoplankton blooms there that made it very easy to see the different structures. In the atmosphere, often it's clouds, so in one of the full disk images I showed you, I was pointing out the different eddies, the different swirls by the cloud fields being moved around by them. But if things were dry, if there weren't any clouds in those regions where there weren't clouds, or in regions of the ocean where there aren't, say, a phytoplankton bloom going on, it's totally the case that there's still eddies and things like that going on that we don't always see.
Great, thank you. And then we have another question. So,
okay, great.
Yeah.
Great. So anonymous attendee asks, were scientists as aware of the spiraling of the atmosphere before space exploration provided the types of data you were showing us today? Yes and no. In fact, rotating tanks were a big part of our understanding of the system before we had all this satellite imagery and the blue marble image from one of the early space missions and these iconic things. Back in the early 20th century, maybe into the 19th century, they were scientists studying Earth and other planets who were using lab apparatus like this, but much bigger and not made out of Legos, to study these kinds of systems. And I think we understood from the equations that we used to describe the atmosphere and the oceans, as well as the observations we took from weather balloons and ships and things. When we put that all together, it was, at least for the specialists, the scientists understood very much that things were swirling, spiraling, that our rotating planet was causing all of this swirling. But it certainly helps everyone, and certainly the lay people, to understand that swirling, to have all this incredible imagery, not just of the real world, but also animations of climate models and weather models. It's yeah, so it's both, I would say. Okay, more questions. Okay, so C Kids, is there a way that wind can carry water in a tornado? So tornadoes are embedded within larger, what are called supercell thunderstorms, and those systems are raining very heavily in general. They come in the summer when the air is incredibly humid and unstable, we call it. And the humid, hot air combined with this sort of lifting creates these intense thunderstorms with tons of rainfall, some of which generate tornadoes as well. So if you've ever experienced like I did growing up in Kansas, like the tornado warning comes, you go in your basement, you're getting barraged by rain for a long time, right? So those are inherently moist structures, even if the tornado, that vortex itself, often is sort of dry.
Yeah, so we have some interesting questions. Yes, so we're almost done here, actually. So we are just about out of time. Spencer, thank you. Is there anything, I think, what would be the biggest takeaway for our viewers today? Is it that sort of keep in mind our Earth is always, we're always rotating, things are always spinning, things are always on the move, even if we don't necessarily see it with our eyes, and why do those movements and constant circulation matter? So what would you say is a big takeaway for?
Yeah, I'll say two things. One, in terms of the science itself and understanding our system, is the world is huge and incredibly complicated on the one hand, but on the other hand, we can use simple models, we can construct simple analogs that help us understand the fundamental parts of it. And that's really the core of science, not just earth science, but all science, is taking these complicated things and stripping them down to their essence and eventually being able to explain them with, toys. And so there's something really wonderful about that, I would say. And then the second part is simply, as a climate scientist, it's kind of a bummer. A lot of times everyone thinks that it's all gloom and doom because climate change is so serious and depressing, and it is. But I wish that everyone could understand how fun and exciting our field is as well. Climate change is one part, and there's so many other things that we do, and they're all fascinating. And hopefully, as the pictures and things you saw today showed, are really striking and mesmerizing. And even the climate change part too, that's a topic for another day, but there's plenty to be excited about, and it's a fascinating challenge on its own. So yeah, we can understand it and it's fun. It's how I'll sum up.
Awesome. So we had two kind of last minute questions that I know we're over time. So if you do have to go, feel free to hop off. But I think I think if you could help us perhaps summarize the, how the eddies, what they're actually made of, and then exactly the types of conditions that need to happen to create one. And separately but related, in the field of geoscience, if you could talk a little bit about jobs and careers and what you do.
Yeah, absolutely. So eddies that's in the singular, it's EDDY, in plural, it's EDDIES. And that's just a jargon for these sort of big swirling things. What they are made out of is basically whatever the fluid is that they're embedded in. So in the atmosphere, you have eddies of air. And sometimes those eddies have air that has saturated the water in it. And so you have clouds as well, but it's still just the atmosphere. And in the ocean, the eddies are just the water swirling around. And sometimes there's the phytoplankton that's riding along with it, and that's how you can see it. But it's just whatever the fluid is that it's made out of, basically. As for what jobs can someone do in this field, so glad to get that question. There are any number of things. There are operational meteorologists, for one, from the weathermen you see on TV to the people that work at the NOAA Hurricane Center that are doing forecasting of hurricanes like Sandy, trying to keep people safe and understand where they're going to go. You have more sort of basic academic research, which is like what a lot of folks at Lamont do, myself included. So I research monsoon systems, which I mentioned at the very beginning. And I try to understand why, sort of basic properties about them, why they exist in places like India. In the summer, they have these intense rainfall from these monsoon systems, why they exist, why they change from year to year, how they might change due to global warming, things like that. In oceanography, there's any number of different jobs that I'm failing to come up with off the top of my head, but these sort of fluid dynamical problems is how we would call them, geophysical fluid dynamical problems, underlie a lot of really cool challenges that are aren't going away anytime soon and need more geoscientists, basically. So yeah.
That's very helpful. Thank you, Spencer. Well, thanks for taking some extra time to answer our last questions. This has all been recorded, and we'll be sharing a list of all the resources and links that were mentioned during the session with everyone when we share the recording, which will either be tomorrow or next week. So we want to thank you for your time, Spencer and Rosalba, and for all our viewers. Thank you for your time as well. And we look forward to seeing you on a future EI Live K-12 session, and hope to see you soon, and enjoy the rest of your day. All right. Thank you so much, everybody. Bye.